don't know the best I can do. Maybe that one put there. Or you can see here is close enough. Right, everyone's good. Okay, we'll do a quick review on semiconductors and we'll move to BJT and CMOS. There are a couple things you guys need to know. Let's get started. So Wednesday there will be a quiz, right? On ADCs or DACs. So it's going to be a similar problem in your homework 1. And homework 1 is due on Wednesday as well. Okay. And tomorrow we are going to do a lab on resistor layout. So you guys are going to use NWell to lay out the resistor string for the DAC and run the simulation. So you can tell you can actually fabricate that DAC, the R2R ladder DAC, because this physically can be fabricated on the CMOS chip during the fabrication. So let's take a look at the semiconductor basics first. And we're going to introduce 2 different devices. So you all know this is a diode, right? And it is literally a PN junction. We'll introduce a PN junction pretty soon. A P-type and an N-type semiconductor being combined together. In the C5 or the CMOS fabrication process, you cannot just directly use the 2 pieces of different semiconductor like this and combine them together and form a diode. It actually looks like this. So you have this is a P substrate. You probably still remember what is a P substrate is from logic, hopefully. And this is NWell. And here you have a P-type material. And you make this connection, This is a cross-sectional view, right? And it's going to form a diode like this. Okay. And another device looks like this, which we haven't covered anywhere in the past. We should do it in analog, but we didn't have enough time because of the pandemic. But now we're going to do this. So this is called BJT, Bipolar Junction Transistor. It has 3 terminals. It is nothing but an NPN. So for this guy specifically, it's an NPN device instead of 2. We call this guy diode, right? Because di means 2. This is transistor, because there are 3 different pieces. It's NPN. And here is a switch. It's called base. This is a collector. This is an emitter. 3 different terminals. It looks like pretty similar to the CMOS, NMOS, or NMOS transistor. But it performs through a different way. So the Unmost transistor looks like this. You have used this at least in your computer logic class to build logic gates, right? So this is the Unmost transistor. Why I know this is Unmost? Still remember that? A trivial question. Why I know this is Unmost? Because there's no little bubble here, right? If I have a bubble, it's a PMOS. And I know this is an NPN transistor, has N on the top, P, N, like this. And here's a collector, here's an emitter. Because this guy, I can see that the little arrow here from the symbol is at the bottom. The counterpart of the NPN is called PNP. It looks like this. Okay, and here's the emitter, here's the collector, here's the base. And it has 3 different junctions, 3 different pieces being combined together. There's P and P. So these are all the transistors that are going to use in microelectronics, in modern microelectronics. So these guys are not being used that often compared to 30 years ago because they consume more power. These ones, there's a dielectric material in between. It's a oxide right behind the gate. So if all the transistors are being put in rest, there's no power consumption, pretty much. There will be a little leakage of current into the gate, but it's tiny in picoamps level or even smaller. But for these guys, it's different. Whenever you have the P and N junction forward biased, remember the P and junction, but I'll cover more details about this pretty soon, okay? Don't worry about that. You know that if you give a positive potential to the diode like this, current will flow into the diode, right? Because this is forward biased. Current is going to flow in the circuit. You probably need a resistor. You have done this in microcontrollers because if this is the LED, it's a different type of diode. You have to use a little like 220 ohms resistor to protect the diode because the current is going to be too high and burn the LED very quickly. Right, so you'll know that if you have a positive potential being shorted to the diode like this, it's called forward biased, then current is going to flow into the circuit. So it's similar to this. You can see that it definitely has a P and N junction here. It's pretty similar to whatever here. It's a P and N, two different types of semiconductors. And if you have a positive potential being shorted to these two junctions like that, the current is going to constantly flow into the junction and it's going to consume power. It doesn't like this. If you just power it up, it's going to be a voltage built up at the gate, but there's no current, right? That's why this consumes more power, and also takes way larger space compared to CMOS. That's why people do not use this anymore to build CPUs nowadays. It used to be super popular, and also you probably have seen this in the past, right? So what is TTL? Have you ever seen this on the back of the machine? And it was for example, if you have used a laser or have used what type of very old any electrical equipment or machines, you can see on the back there's a TTL input or serial port input. Not just all USBs, I understand that, but in the past, you probably can see the real old machines. You go to the lab, we have something like came from the 70s. You can still see that there's a serial port, even a parallel port. Can you imagine that? An input port looks like the VGA, but way larger than that, has all the ports, the pins, like over 40, 50 all the pins, and they're running in parallel. So it's like you give a data to them in parallel at every clock, and the digital system inside is going to sample that. We don't use parallel anymore. We just use serial communication right now. Why is that? High enough frequency, and parallel takes a lot of pin resources, right? It has 40 pins. If you have a 64-bit CPU, you need a 64 bits or pins to get it done, to get the job done. So, but serious, if you have a serial communication, you can have just one pin and just clock it, use a specific communication protocol to finish all the cycles. So it can save a lot of space on the chip, which is critical. And TTL means transistor logic. It's not the CMOS logic, it's transistor logic. And in the old days, they use all these BGT transistors to build all these computer logic, AND gate, OR gate, like that. And this type of transistor is being driven by the current flows into the base. This is called the base. So whenever current flows into it, it's going to induce a current amplification from the collector flow to the emitter. So you get a current flow in that direction and being amplified. So it is actually a current controlled current source. Right? It's a current controlled current source for BGTs. If you heard current controlled current source, you know current is always flowing, which is bad because it's consuming power, low power. This is a voltage controlled current source. Why is that? Because you can imagine, still remember the IV curves? So for the CMOS, here's ID, which is the drain current, and this is what? VDS. So after a specific VDS, the current is not changing too much. So we can consider this as a current source because it's not changing anymore. It's providing a constant current value. So this current is being controlled by voltage. That's why it's called a voltage control current source. So all these guys are voltage controlled current source, but these BGTs are current controlled current source. Remember that. Okay. Just a really quick overview about what are all the devices we're going to use and being used in modern electronics. But these guys are still being used in some of the devices which is not really power sensitive. You don't care about the power really much. And for example, what's the name of the op-amp? 741. Remember that? It's from TI, and that kind of op-amp is totally built by all these BGTs. But for the 324 or something, I think that's from LT. I forgot. So these ones are based on CMOS transistors, but these ones are totally built by BGT. So the performance is low, the power consumption is high, and the size of the footprint of the chip of the circuits is relatively larger compared to the CMOS devices. Okay, so now let's take a look at the details about every single device here. Everywhere, pretty much. Yeah. Even the FinFETs are actually CMOS. It's just a different structure. You know, here is a cross-sectional view of the standard CMOS. Until like 20 nanometer, I think they are always looks like this. So here's a gate, here's a source, here's a drain, right? But whenever, so what is this dimension here for the CMOS? Length or width? Length, because the current is being conducted in here, right? It's being charged up and discharged in here. So that's the channel length. And whenever we are talking about 20 nanometer, 180 nanometer, 500 nanometer, so it means the size of the lens, right? And you hope the lens to be shorter, so you can charge and discharge every single transistor faster. That's why your CPU can run faster. But the downside is it's going to generate a lot of power and heat. So the power consumption goes up and heat generation goes up. So I have to manage the heat on the chip. Sometimes use a different cooling strategy. You know, that's all totally another different research field. You can see a lot of people are dealing with heat management on the chips. So whenever this is getting smaller and smaller, you can imagine, I just physically imagine like you have a CMOS device in front of you, and it just make the lens smaller and smaller like this. What about that? What's going to happen? What you think? I mean, if you still have the standard CMOS fabrication process, but you have a tiny lens here, let's say 10 nanometer. So 10 nanometer is not even the most state-of-the-art technology. I think what we said in the past, a couple of weeks ago, like 3 nanometers, probably will be available next year, TSMC and Samsung. So whenever this is getting smaller and smaller, what's going to happen? The gate is going to lose its control over the channel. So it cannot effectively control the on and off status of the gate, of the channel by using the gate. So what's going to happen is I have to make the channel a 3D structure to make it like a bump like this, and have the gate being fabricated surrounded like this. So for example, something like this, you have something on the top of it because the channel is super thin right now, right? Super thin. I have a gate floating on the top because there's a little oxide layer in between, right? It's not even touching the channel, so it's on the top. And you want to use the gate to control the on and off status of the channel. It's going to be harder and harder whenever this is being scaled down and it's getting smaller and smaller, right? So what you want to do is just fabricate a channel in a 3D structure and have a gate to wrap it up like this. So you can use the gate effectively control the channel on and off states, right? Like this. So this guy, the channel structure like this is called a fin. Right? Looks like a fin. So that's why it's called FinFET. I forgot, like FinFET starts from which size? Maybe 10 nanometer, 7 nanometer. You probably have to start using FinFETs instead of the regular CMOS application. And so that happens starting from 7 nanometer, and then the 5 nanometer, 3 nanometer becomes available, and they find out FinFET is still not ideal. So what's next? So you have something. So here's a fin, right? Here's a fin. Here's the length of the channel. That's the length. That's the length of the channel. Right? Here's a gate. Right? Here's a gate. Okay? So I can give a voltage to the gate so the electron can conduct through the length of the channel. But still not good enough for 3 nanometers. You don't want a fin. What's next? You can imagine. For 3 nanometer, Samsung developed. It's going to be available in 2 years. So they're not using fin anymore. They start using wires. So channels are wires. So this is the fin. This is the wires. They have wires like this and have the gate not just wrap it up like this, right? It's going to totally wrap it up like this. Some of the extreme cases for 3 nanometer technology. So have like this. So have full control of the channel. That's a 3 nanometer technology. It's not even FinFET. It just happens in 3 years. You know, so FinFET is not new anymore. 3 years before, so FinFET, oh, that's the best technology you can do for 7 nanometer. But now, just 3 years later, no, it's not the best. So have to use wires like this. So have full control of the gate. Okay. All right, let's do a quick review on semiconductor because some of you guys were not in analog and you were in logic. However, it's been a while first, and second, we didn't do that much at that time. So still remember, the first thing you need to know, the number of electrons in each shell. You still know this? Electrons in each shell of the atom. Is 2n squared. Right? Don't ask me why, because I don't know. The physics is going to answer this question. Quantum mechanics. It takes a whole semester to. It's an entire course for 1 semester. Okay. So in that case, we know that how many protons a silicon atom has. Remember, or do you know that? Let me just tell you, it's 14. So in that case, the first shell has, when n is 1, you're getting 2, right? And for the second shell, is 2 times 2 to the second. What is that? The first shell, when n is 1, you're getting 2, right? The second shell, when n is 2, how many electrons it has? 8. What about the third? 18 should be the maximum, right? Because 3 to the second will be 9. 2 times 9 is 18. But however, this guy only has, so silicon only has 14 protons in total. So it shouldn't be 18 here. Maximum, the capacity is 18, but however, it only has, silicon atom only has 4 electrons at the outer orbital. So these 4 electrons here is called valence electrons. Because it's involved in valence bonds with other atoms, right? So what about copper? Couldn't pronounce it. Copper, sorry. Copper is 29, if I'm correct. It's 2, 8, 18. What about last one? Yeah, that one, because 10 plus 18 will be 28, and only has 1 left. So only has 1 left as a valence electron, so it tends to lose it and becomes positively charged, right? So that's why it's a metal. So it's a conductor. And this has 4. It's not that easy to lose all the 4 electrons. So it's not really conductive. So it's called semiconductor. And there are two main types of semiconductors. The first type is called elemental semiconductors. For example, silicon or germanium. Another type is called compound semiconductors. For example, gallium nitride, gallium arsenide. So AS is arsenide. Or gallium phosphorus, like all these materials, compound semiconductors. It's compared to this one, the elemental semiconductors, right? And if we directly just use a silicon for our chips, that won't work. Why is that? Just grab a piece of silicon and directly build a chip on that without the post-processing. What's the problem? Yep. So the conductivity is too low, right? We do need a semiconductor, but the conductivity of the original silicon is too low, just too low, right? So we want to dope it with some dopants to make it more conductive, and you can control the conductivity by adding a different concentration of dopants. So what are the 2 main dopants available? Phosphorus and boron. So phosphorus how many protons it has for each atom? 15. Two. Do we have 8 here at the second shell? What about third? 5 left. Okay. So for a piece of silicon, if I grab a piece of silicon, pure silicon, I can see the crystal lattice looks like this. I just didn't draw all of them because it takes the entire semester, even longer to draw that. Billions of atoms. And they share the electrons with the adjacent electron atoms, right, like this. So we just look at the one in the middle, and you know that it's repeatable, can be extended to all the other atoms in the lattice. So this guy has 4 free electrons in the, so 4 valence electrons, let's say that. Okay, it's being shared with another 4 atoms, silicon atoms like this, right? If we dope this pure silicon with phosphorus, and for example, the one phosphorus atom replace this silicon in this lattice like this, because phosphorus has 5 free electrons, free valence electrons. So after formed all these covalent bonds like this, so these are called covalent bonds. There's still 1 electron available after that because it has 5 in total. It's going to be a free electron. And that's why we call this type of semiconductor an N-type semiconductor. So you can remember this by thinking about it's a negative, right? So the electron takes a negative charge. It's an N-type semiconductor. And if we dope a silicon, pure silicon with boron, something different will happen. Boron in the middle, and boron has 5 protons. So it is, so the valence electron for each boron atom, so how many valence electrons it has for every single boron atom. There are totally 5 protons, right? So how many valence electrons, which is the electron number of electrons here, right? 2, 3. So which means after you dope this pure silicon with boron, so 3 of the electrons from boron can form covalent bonds with the 3 adjacent silicon atoms, but just 1 here is different because it only has 3 valence electrons. So here we'll not have another electron to form the covalent bonds with this silicon atom. So what's going to happen is going to leave a hole here, but this silicon still have an electron here. It's just because the boron does not have an electron to fill this hole. So a hole here is the absence of electron here in the lattice. So this is a hole or free hole will appear in this mixture. We call this type of semiconductor a p-type semiconductor. All right, so these are the 2 main types of semiconductors we have. Any questions so far? No? All right, more concepts. there's a concept called Ni. So what is Ni? I means intrinsic, N means, okay, just number, right? So Ni means it's a number of free electrons and holes in an intrinsic silicon, which means not doped silicon, in each unit volume, which is per cubic centimeter at room temperature. Remember all these conditions, right? If you miss any of the conditions, this will not be the case. At room temp. Which is 25 Celsius. See if I'm missing anything. The number of free electrons and holes in an intrinsic silicon in each unit volume. I should say this first, right? So number of free electrons and holes in each unit volume in an intrinsic silicon at room temperature. Right? So N is the number of electrons, concentration of electrons. Or free electrons. P times P. P is the concentration of free holes. Why do you have free holes and free electrons? So N times P equals to Ni squared. Here's a quick question. Why are there free electrons and free holes in a piece of silicon? So here's a piece of silicon, okay? There are electrons and atoms, right? But the electrons can leave that spot and have a hole left at that spot because of temperature. It's a thermal effect. And at the absolute zero temperature, there won't be any free electrons and holes, but however, any other temperatures, there will be free electrons and holes, because whenever the equilibrium is achieved, the recombination rate equals to the regeneration rate and there will be some free electrons and holes, because normally you should have a hole with an electron in there. It should be always like that. Whole lot of holes and electrons, because they are separating and being recombined all the time. At the equilibrium, the rate of the electron and holes are combining equals to the rate they are being separated. Okay, so that's called equilibrium, but there will be some free electrons and free holes in there. You know what I mean? So there will be holes, electrons, holes. Electrons is dynamic, they are always being recombined and being separated all the time. But the rate, these two rates are equal to each other. And there will be some free electrons and holes. And these are the concentrations. And here is a equation to that dominates this behavior. N times P. So N is the concentration of these guys. P is the concentration of these guys. N times P equals to this. Keep in mind. Just want to remember that. And for this number, Ni, and for silicon, and at room temp, it equals to 1.5 times 10 to the 10th per cubic centimeter. So this is the number you want to use. And this not only works for intrinsic semiconductors, also works for extrinsic semiconductor, which means a piece of silicon is being doped with either phosphorus or borons and still follow this rule. So this works for both intrinsic and extrinsic All right, let's see some examples. For example, if we have a piece of silicon and we dope it with phosphorus, and we can call the phosphorus is a donor. Donor of what? Electrons? Is that true? Because the phosphorus atom contributes one more free electron. So that single word in general, so the phosphorus dopant is a donor. Okay, for boron, it's called acceptor. Electron donor, electron acceptor, because it has a hole, a free hole here, ready to accept more electrons. All right. So if we dope a piece of silicon with phosphorus, and we know that because we can control that fabrication process, and we know that the concentration of phosphorus we have doped into that silicon. Look at the number 5. Concentration of boron atoms. Items. It's called ND. It's donor, and it's an N-type. It's contributing the negative charges, right? N-type or negative. You can just use this way to remember it. And ND is approximately equal to the N-type semiconductor and the concentration of electrons. So here's the N-type. And here is a concentration of electrons. Or electrons, just say electrons. So this is electrons, concentration of electrons in the N-type semiconductor. Why is that? Because every single phosphorus atom contributes one electron, one free electron. So that's why they are equal. If you dope a piece of silicon with phosphorus, then there will be more electrons compared to holes. And we call the electrons are the majority. and this is the minority in that semiconductor material. Because these are similar, and this is normally given because the engineer just did it. And we can calculate the concentration of holes in that N-type semiconductor by following this equation. Because I just told you that this works not only for intrinsic semiconductors, but also for extrinsic semiconductors. So this is not intrinsic because this piece of silicon has been doped with a donor, which is phosphorus sometimes. And these are equal, and N times P, both in the N-type semiconductor, equals to Ni squared, and Ni is the number of free electrons and holes in intrinsic silicon, which is given. Okay, so the N-type, the holes concentration in the N-type semiconductor equals to Ni. So from here, right? From here is N equals to Ni squared over N like this. It's N-type and electron concentration. This guy equals to this, which is given. So this is also this equals to this, Nd. So you can calculate this value using this equation. All right, let's see an example here. Yeah, before we move forward, let's do the acceptor one as well. For the p-type, concentration of acceptor items. It's called Na, and Na is approximately equal to what? Same concept. Here, Nd equals to the N-type. It becomes N-type because it's a donor. And that's the number of electrons, which makes sense because every single donor atom is going to contribute one free electron. So Nd is pretty much Nn. So for the acceptor, for the p-type, positive, right? P-type. Na is pretty much what? Np? Is that making sense? Is that Np? Why is Np? For Nd, it's a donor, equals to Nn, because it's N-type and electrons concentration, right? So for the p-type, it's going to be Na equals to P, which is the holes concentration, because every boron atom is going to contribute one free hole. So definitely it's a bigger P and smaller PP, right? PP. That PP? Should be PP because of p-type. So here's p-type, smaller p is p-type. And the bigger p is going to be the concentration of electron holes. It's a boron. Boron contributes the hole to the compound, to the mixture. So here again, Na is what? PP. That's p-type. That's concentration of the holes. So I keep saying concentration means what? The number of holes in 1 cubic centimeter, right? It's a concentration, or you can say just the number of electrons but in unit, every unit volume. And depends on what we just mentioned, that N times P equals to Ni squared. And we know here this is given, right? Controlled by the engineers. So we know that P, I know it's a p-type P, but it's still a P. So P times what? So P times what? Equals to Ni squared here, in this case. It's still the same type. So definitely you know this, it should be a smaller P. What about here? N. They are both p-type, and since we are evaluating the same material, the p-type. But here is the holes, concentration of the holes is concentration of the electrons. So still N times P equals to Ni squared. And because this is given, right? So we can calculate, is NP here minority or majority? Is minority, because the holes, they have a lot of holes here. So have acceptors being doped into the silicon. So NP equals to Ni squared over what? PP, or Ni squared over Na. And this is given. This is given. To calculate the concentration of electrons in a p-type semiconductor. Okay. One example, the N-type silicon. Dopant concentration is like this. ND equals to 10 to the 17th per cubic centimeter. So I'm asking you to find electron and hole concentrations. At room temp. Which is T equals to temperature equals to 300 Kelvin. Or you can say it's 25 Celsius, it's the same thing. N-type or P-type? N-type. So it makes sense because of donor. And we know that for the N-type semiconductor, ND equals to what? NP, PN, PP, which one? NN. And we also know that NN times NP, PN, NP, PP. What's that? That's my job, to confuse you, so never mind. NN times what? PN. At least there should be N because they are all N types. They are both N types, right? Same material, N type. So NP equals to Ni squared. And we know that Pn equals to Ni squared over Nn, which is also this over Nd. And we know that Ni squared is actually 10 to the 15th. 1.5 times 10 to the 15th. 10 to the 10th, sorry. Square over 10 to the 17th, which is 2.25 times 10 to the 20th and 10 to the 17th, which is 2.25 times 10 to the 3rd. So what's the unit? This many individuals of holes per cubic centimeter, like this. All right, so that's the concentration. You just put another statement at the end in the homework. So of holes is and concentration of electrons is, right? So you can put it there. Is it everything I ask over here? Concentration, oh yeah, that's it. That's how you deal with this type of problem.
How to do the concentration of the electrons?
Here. You probably are wondering, like, the intrinsic silicon must have some electrons over there at the very beginning. After you dope it, why do you just directly use ND, not considering the original electrons there at the very beginning of the intrinsic silicon? To fill, right? To consider. The donor is going to dominate. You can see how it's a 17th range. But you can see it's like 10 to the third. You want to consider it? Probably not. It's pretty much just this value. It's too many. All right, so these are not super accurate values. It's just like pretty much, it's just very close to the reality, the real values. All right, that's it. We'll see you tomorrow in the lab.